Yes, today I'm going to present a body biasing injection attack on a recent SoC. And the main idea is to attack the hardware AES Accelerator of this chip using body biasing injection. So the motivation behind this presentation, actually, I'm going to ask you a question. If anyone here is familiar with electromagnetic fault injection? Okay, this is cool. Anyone here is familiar with body biasing fault injection? Only 3. Okay, so this is my motivation, actually. Body biasing injection is a certain of a recent fault injection attack. It's not very well studied in the literature. I think there are only 2 or 3 papers that describe this kind of attacks. So this is why, actually, I'm trying to investigate this attack. And recently, I have seen a lot of devices that have been deployed in the market, such as hardware wallets, for example. And my role is to evaluate this kind of wallets against fault injection and side channel attacks. This is why investigating new attacks is very important for me. So I'm going to talk a little bit about fault attacks. Why we need faults? Why we perform faults, actually. So the main idea of injecting faults is to perform a perturbation during the execution of sensitive operations. For example, if you are performing secure boot and you are injecting faults during the secure boot, there is a possibility of bypassing the signature verification, for example. The same if you are performing crypto operations, like AES, for example. You can inject during certain rounds of the AES in order to extract the key using differential fault analysis. So you can find here a very interesting paper about a guy who already attacked the AES of PlayStation using differential fault analysis. I don't know if you know this paper or not, but it was very interesting, actually, to show a practical attack. Power glitches. Power glitch is considered one of the fault injection attack techniques. It's a very low-cost technique. You can implement it using a MOSFET, for example. The main idea is to drop the voltage level of the chip to a very low level. However, there are some challenges while you are performing power glitch attacks. The main idea of the first challenge, actually, is that the effect of the glitch is very general on the chip itself. For example, if you are attacking a complex SoC and you would like to target the crypto core of the chip, it's very difficult. You'll find a lot of pins for different VDD, and you don't know exactly which one you have to glitch. And even if you are glitching the correct one, you won't be more precise. The second one is electromagnetic fault injection. And the main idea is that you have a very high voltage. You are going to apply the high voltage into a coil, trying to generate electromagnetic, and this electromagnetic, when you touch the probe or the electromagnetic probe of the chip itself, you're going to create perturbation. Well, if I'm talking about EMFI, it has to build a setup. It's a medium cost. If you compare it, for example, with glitches, it's not low cost compared to power glitches, but it's cost. It's between, actually, the laser and power glitches. The third one is laser attacks. So it's very expensive. If you would like to do it, you need to decap the chip. In order to find the substrate, you can decap the chip using a front side or back side. The main idea is that you hit the surface of the chip using a laser beam, and the laser is going to induce current, and the current is going to change the state of the transistors from 1 to 0, trying to create errors. As I said here, you need to decap the chip. It's expensive. It needs more experience as well. Now, let me discover body biasing injection with you. So the main idea of body biasing injection is to apply a high voltage into the surface of the chip using a needle. So the main idea is that the needle is going to bypass a current to the surface of the chip, trying to create errors. It was proposed by Philippe Morin in 2012. And this kind of fault injection techniques, you need to decap the chip itself. So almost it needs the same preparation like laser attacks. And the effect of the BBI, I can say it's like a localized ground glitching. Why it's a localized ground glitching? So if I'm going to describe, actually, the silicon model, which was proposed by Philippe Morin. You can see here, for example, if you are going to inject a high voltage here into the substrate, the main idea is that the ground of the CMOS is going to change as well. The same for the VDD of the CMOS, and if you will find the difference between them is like a glitch. However, it's a localized glitch. Why? Because the R of the substrate is changing from one point to another. Well, in Cardis 2020, actually, there was a very nice setup which was presented by Colin. It was a very, very low-cost setup. The main idea is that you have a very small voltage, which is used to charge some capacitors. And during the injection times, this voltage is going to be increased using a transformer. And after that, you are going to touch the surface of the chip using a needle, which is connected to the transformer itself. So it's a very, very low-cost setup. It's very interesting. So I started to think about this, setup, and to build it in our lab. It's very interesting while you are performing fault injection to have the double polarity. It's very important to have a positive pulse and negative pulse. Why? Because if you are injecting a backside, you may need the positive pulse, but if you are injecting on the front side, you need the reverse polarity. And also you can find some points on the surface of the chip which are vulnerable to the positive pulse, and also other points which are vulnerable to the negative pulse. So I'm going to solve this problem in the design of Colin, because it doesn't support this flexibility. And also there is an external power supply that I'm going to add to make the setup more portable. Just plug it to the USB itself, and you don't need external power supply. So this is my design. The main idea is that you have the main idea is that this is a design of Colin, which is in red. I just added an onboard VCC that may come from an IoT chip or an MCU, for example. And after that, I added a charge circuit in order to charge this VCC on a controlled value. So you could have the ability to have a flexible voltage, so you can change it if you want. And also a discharge circuit in order to switch off the injector if you would like. And also in terms of the polarity, you can see that I take the 1 point from the secondary of the transformer and connected it to the positive, and also the negative is connected to 0.2. And if you would like, for example, to inject a positive pulse, you can inject this point to the needle and the negative pulse to the ground of the chip. And if you would like to reverse it, will be more flexible. So this is a final PCB that I already did. You can find that here I use a Arduino Shao, which is an MCU that you can use to control the charge and discharge. And also it can feed the circuit with a VDD with 5 volt maximum. Here there is an SMA connector for triggering the voltage, for triggering the fault injection. And here, for example, there is a needle, it's connected to the positive, and the negative here is going to connect it to the ground. But if you would like to reverse the polarity of the voltage pulse, you can connect it to the negative, and this positive is going to be connected to the ground of the device itself. So you can see that I have an MCU that can deliver 5 voltage. The turns ratio here is 500. It's 50. So we can obtain a programmable voltage until 250 volt. I already obtained the dual polarity, so we can inject positive and negative pulses. So I would like to thank my teammate Olivier for supporting soldering the small components here, because I'm not very good in soldering electronic components. So you can find here that I already proved that I have a flexible voltage that I can change it very, very easy. So if I'm going to here on the x-axis, this is number of pulses. So if you increase the number of pulses to charge the capacitor, so I have a programmable voltage that can start from lower than to 1 until 5. So if you multiply it by 50, you will obtain a programmable voltage until 250. So I need now to verify and validate exactly if my injector is able to inject errors or not. So this is why I'm using a device under test, but I don't like to talk about the name of the vendor for the moment. So I'm using a low cost and low power SoC. It contains a Wi-Fi and Bluetooth interfaces. It's fabricated on a 40 nanometer technology, and recently it has been deployed in hardware wallet. This is why I'm interested in this chip. So the first thing to validate the design is the design of the injector is that I did already a glitchable application. So just to see if I'm going to modify the value of this counter during counting. So I'm going to inject a fault here. The main idea is to scan the surface of the chip here from the X and Y. I'm trying to inject faults during the execution of this code, and especially the counter part. So I'm going to run the glitchable application that scans the overall surface, and I'm going to try the dual polarity of the voltage. My setup, if you can see it, so you can see on the right here, this is the injector. It's on the top of the chip. The chip is decapped, of course. You can see it here. And I have a table, very cheap table to move the probe XY. And I have an oscilloscope in order to register the power traces and to see exactly what happens while I'm injecting faults. Sometimes I have external power supply here. There are some chips that maybe 250 voltage is not sufficient for faulting, so maybe I will need the help of the external power supply. So I already obtained successful faults when I have a positive pulse. So I obtained the zone that I already was able to skip from the loop to modify the value of the counter. However, for negative pulse, I obtained some faults, for example, in this zone, and also some separate points here. You can see that there are some physical locations on the chip which is vulnerable to positive pulses and also negative pulses. This is very important while you are doing a fault injection evaluation, especially if you are targeting, maybe if you start the evaluation, you inject a positive pulse, you are targeting, for example, the crypto core, it doesn't work the attack, so you have to change the polarity of the voltage. As I said, I use the oscilloscope in order to register the power traces. So here, this is my code without injecting any fault. There is a loop here. So the chip here is doing nothing exactly, just counting. So after that, there is a communication to send the value of the counter that was counted. So I'm going to inject here a positive pulse. You can see it, that it's negative. It looks like a negative glitch. And after that, the chip goes for the same activity like here, but in this case, I already modified the value of the counter. If you inject a negative pulse, the effect will be positive here, and the power trace, you can see that it's cut in a very short time compared to this one, but I already modified also the value of the counter. Let me talk about the hardware AES Accelerator. This is a chip actually. Contains a cryptographic hardware accelerator such as ES, SHA, RSA, elliptic curve, random number generation. And also it contains the ES 128. Actually, the ES accelerator, you can configure it from 128 till 256. So this is the main target is to break the ES using body biasing injection. I started to measure the power consumption during the execution of the ES. So I'm very sorry I won't be able actually to show the firmware that I called the ES because it is the name of the vendor. You can know the name of the vendor from the firmware itself. So here is the ES, which is executed. So in my firmware, simply just I raise a trigger, and then I call the ES, and then the trigger value will be low, so I will be able to know exactly where the ES is executed. But here in this trace, it's very difficult to identify exactly where the ES is executed. So this is why I performed something called leakage detection using a signal to noise ratio. For example, here, this is the scenario on the keys. So you can find here the keys are loaded. And here is the plain text. And on white, the ciphertext is loaded. So in between the loading of the plain text and the ciphertext, the AES is executed. So now I know very well that the AES is during this time period. So I have a very short timing window for injecting faults. Otherwise, the experiment will take a lot of time. So now I already reduced one fault parameter, which is the offset that may increase the time of evaluation. The main idea that I would like to perform a differential fault analysis. There was a very interesting paper published in 2003. The main idea is that if you can inject a fault, for example, this is the AES, this is round 9, and this is round 10. But if you are able to inject a fault before the mixed colon of round 9, so the fault will be propagated in the overall colon after the mixed colon, and by the end it will be propagated using this figure. Actually, you will find that the first byte is modified, and after that you will find that it will be like a diagonal modification. To perform this kind of attacks using DFA, if you are able, of course, to inject a fault in only one byte before the mixed colon, what you needed just to attack one colon key, you need two faults per colon here. That will help you to attack the overall key of the AES. Well, so I started to repeat the same experiment. I have the AES which is running. I already know where the AES is executed, and I started to scan the chip. So you'll find here I obtained some faults using the maximum voltage of the injector, which is 250 volt. So here I obtained some faults, but unfortunately the faults that I obtained, it's like only on the ciphertext itself. So the output is like the ciphertext, and I already modified some ciphertext values while it's zeros or 1. Okay, so only 4 bytes of the ciphertext. So it seems to be like the communication of the ciphertext. So it's the MCU. I think the MCU. I already faulted the MCU in this case because it's used for loading a value into the register. However, after that, I started to think that the 250 volt is not able to fault the AES crypto on the chip itself. So I started to think about increasing a little bit the voltage. So this is why I use the external power supply. So you can see that, okay, with 250, I was able to fault a CPU application for this chip. But after that, I used an external power supply to give me 10 volt. And now I have like 500 voltage that I can inject into the circuit itself. I spent some time to optimize the faults in order to inject only faults for the AES and only in round 9. So I found a very interesting spot here that I obtained already a success rate like 60% that I'm able to fault the AES itself. So this means that the AES crypto core is here, but it needs more voltage. Okay. So you can see here, I already registered a power consumption trace during the successful fault of the AES. So here is the effect of the body biasing injection, actually. However, this point is saturated because the vertical resolution of the oscilloscope was like above the maximum. So this is why you can find this value is cut and flat. You can see here on the right, there is a map that shows that how many times I faulted single byte for every colon. You can see that I'm already above to 80% faulty cases per colon. So I have a lot of interesting faults to perform the differential fault analysis. So I was able actually to attack the overall key of the AES using this result. I have some notes during this experiment. If you are going to try this kind of attacks, you have to You have to be careful. If you are injecting a high voltage into the substrate itself, you are going to damage the chip. I already damaged 3 chips. And also, it's very important while you are doing decapping the chip, you have to be careful also because you may damage the chip itself. And also, you have to avoid moving the needle on the X and Y while you are not while you are in touch with the chip, because also you are going to damage the chip. So it's better to, if you would like to move while X and Y, you have to move up a little bit the needle and then move it while X and Y and then make it down again. So the conclusion. So I already built a cheap and the compact setup for BBI. I use this the homemade injector to break the hardware AES Accelerator of a recent SoC. I just need only 10K trials to dump the overall key of the AES. The silicon baguette, which is my injector, I'm going to release it in a few days on the GitHub. Regarding the future work, actually, I'm going to evaluate more SoCs using this technique. And also, I'm going to study the effect of this voltage injection, of this injection technique on secure elements, where you can find some glitch detectors and try to see exactly what happened. Yeah, thank you very much. I don't know if you have any questions. Yeah.
What was your reference signal for your trigger? You're
I can control
firing at a specific time relative to something else.
I can control the trigger from the firmware itself.
So you've modified this firmware.
Yes.
Custom firmware?
Yeah. The hardware accelerator, you can call it from a firmware, from the firmware, yes, but after that you can easily add a trigger before and after the launch of the start of the AES. Yeah.
I see.
Yeah.
How reliable is this? Like if you were to, tear apart the setup and then try and go back and find that spot again?
I can reproduce that very easily. If you can find here. This is the chip after the experiment. Here you can find that I injected a lot of faults here because this is the fault where I already obtained for faulting the communication of the ciphertext. But here there is a yes, and this point is where the crypto core is on the chip itself. Yeah.
Do we have any more questions?
Yeah.
A very interesting talk.
Thank you.
So from this picture, it's a little hard to tell if this is the back side of the chip or the top side. I'm assuming
this is the back side of the chip.
Okay, and was it BGA? So you went through the PCB and then into the lead frame?
Sorry?
So are we looking at the back side of the PCB and you've gone through the PCB, through the lead frame?
I didn't hear you very well. Sorry. Okay.
I'm just wondering what we're looking at. If this is the backside of the chip, shouldn't there be BGA, or is this?
It's an SoC. It's a microcontroller. It's an SoC for low power, which is used for low power applications. But it's not an FPGA. No.
No, I mean, so you've gone through the PCB, and I was wondering if there's metal contacts in there, and then it looks like we're looking at the lead frame that the chip is mounted on.
Yes. The chip, the chip actually is soldered on the backside of the PCB itself.
Okay.
Okay.
Yeah, then there's nothing. Yeah, you're not interfering with any signals. Yeah. Okay.
Maybe I didn't like to show the overall setup of the PCB because we have a talk at Black Hat, so we will show that there. So.
Okay, that makes sense. And if I'm understanding correctly, did you say that you can also do body biasing through the top side of the chip?
Yes, on the front side. Yeah, but decapping the chip from the front side is very challenging because the bounding wire needs some preparation. And in the lab, we don't have this tool for the moment. This is why we use the backside.
Yeah, and do you have to remove the passivation oxide, or?
Sorry?
Usually there's a passivation oxide that's deposited on top.
Yeah. I mean, you have to be careful because you shouldn't remove if you are performing a front side decapping, you have to be careful actually, because the bounding wire, if you cut one wire, it's okay. It's done, the chip. So I haven't done before a front side decapping. Maybe Olivier Thomas, he's here, he can.
Yeah.
I can do it, yeah.
Any other questions?
Yeah.
No more? Then please another round of applause for Karim.
Okay, thank you very much.